Hi, welcome to the second video in my series on ladders leaning against walls. And in this particular problem, what I'm going to do is extend the work that I did in the first video, where we've got this time a ladder leaning against a smooth vertical wall here, but it's on rough ground. And it's just on the point of slipping. So this is a problem that involves friction. So to do this, let's just go through this example up here. What we've got is a uniform ladder of length 2L, and it's got a mass of 20 kilograms. It rests in equilibrium with its base on a rough horizontal floor and its top against a smooth vertical wall. The ladder is inclined at 60 degrees to the horizontal, and if the ladder is on the point of slipping and the coefficient of friction is mu, find the value of mu and the reactions at the floor and at the wall. So if you haven't got a sketch in front of you, you've obviously got to draw one, and so you'd have your ladder then leaning against your wall and the floor. And we've got it inclined at 60 degrees then to the horizontal. Now it's a uniform ladder of length 2L and mass 20 kilograms, so the weight is going to act in the middle and it will act vertically downwards. We'll mark that in then as 20G, 20 times G newtons. And in this problem we'll take G as 9.8. What other forces would we have? Well, there'll be a reaction from the ground here that will act upwards, a normal contact force. Let's call that, say, R1 newtons. There'll be a contact force from the wall here that'll be acting perpendicular to the wall, and we'll have to call that, say, another reaction. It won't be the same as this one. We'll call it R2 newtons. Now, the ladder is resting on rough ground and it's on the point of slipping. So if the ladder were to slip, it would want to slide out towards the right here. So friction must oppose motion, so it's going to act inwards to the left. So just mark that one on, that force there is the frictional force. And if it's on the point of slipping, that frictional force is going to be equal to mu R. In this case the reaction though is R1, so it's mu R1. Just put the units there of newtons in. That's it for the forces. There's no friction acting on the wall here because the wall is smooth. We need to put some other information on. We'll put that the ladder was a uniform ladder of length 2L, so that's going to be L there and L there. Now we've got to work out what mu is, what R1 is and what R2 is, the reactions at the wall and at the ground. So what we've got here is essentially three unknowns. So to do a question like this is going to mean that we need to create three independent equations so that we can solve them simultaneously. So where are we going to get those three equations from? Well, with problems like this on equilibrium of a rigid body, what we would normally always do is do moments. So that's going to be one equation, and we can take moments about any point we like. We don't generally do another moments equation about another point because that wouldn't necessarily be an independent equation. So we do one moments equation and we get the other two equations from resolving vertically and horizontally. And that's the typical way to go with these kind of problems. So I'm going to first of all then resolve in a vertical sense. I'm going to take upwards as positive. Doesn't matter whether you go upwards or downwards as positive, as long as you stick to it. Okay, so if we resolve upwards, what forces have we got? Well, we've got all of R1 acting upwards, and we've got the weight 20G newtons acting downwards, so that's minus 20G. As for R2 and the frictional force, mu R1, they're perpendicular to this vertical direction, so they won't come into this equation. And so because this is the resultant force acting on the ladder's in equilibrium, that resultant force must be equal to 0. So if I rearrange this to make R1 the subject, it follows that R1 must be equal to 20g. And if I take g to be 9.8, it turns out then that R1 equals 20 times 9.8, that's 196 newtons, okay, 196 newtons. So there's our first force, our first contact force here, okay, the reaction with the floor. We need another equation, and we get that from resolving horizontally. And you can resolve horizontally taking left or to the right as positive. I'm going to take to the right as positive. Again, it doesn't matter. If I take right as positive, then I've got all of R2 acting to the right. And then I've got the frictional force, mu R1, which acts to the left. So that'd be minus mu R1. As for the weight, 20g, and the reaction from the floor, they're perpendicular to the horizontal direction, so they won't enter into this equation. So again, this is the resultant force acting on the ladder. It's in equilibrium, so that resultant force must be 0. And we can rearrange this now for R2 by adding mu R1 to both sides, so it follows that R2 must be equal to mu R1. But we know that R1 is 196 newtons, so again it would follow from that that R2 must be equal to 196 mu if I substitute that into there. Okay, so I've still got R2 and mu to work out, the coefficient of friction here. So I'm going to need another equation. And that equation, as I said earlier, comes from taking moments. And we can take moments about any point we like. And I would encourage you to experiment with this, to take moments about any point. I'm going to take them about this point here on the bottom. Okay, let me call this A. I'm going to take moments about A. Why am I going to take moments about A? Well, it's just purely that I can see that two of these forces pass through A, so there's going to be no turning effect about A, no moment about A produced by these two forces. It'll only be the weight and the reaction up here. So my equation that I build here is only going to have two terms in, alright, involving the weight and the reaction here. Whereas if, for instance, I took moments about this point, I would have the weight, the reaction, and the frictional force in my equation. Three things that I'd have to consider, as opposed to doing two if I take moments about this end. But as I say, do have a go at this question again. Take moments about this point here, and you should arrive at the same result at the end of the day. I need to set up a sense for the moments about A, and I'm going to take clockwise as positive. Again, it's up to you which way you take. So if I take moments about A clockwise as positive, it's like taking a ruler here and holding or putting your finger at this point here, and then if you push in these directions, okay, you can see which way the ruler would want to turn, in this case the ladder. Now I've got forces that are inclined at angles to this ladder, and in the previous tutorials I've shown you how I deal with these. What I do is I consider forces at right angles to the ladder. Okay, I split the forces into components. Now I'm going to look at splitting the force R2 into two components. One will be perpendicular up here, okay, to the ladder. The other one would act down the ladder. When it comes to the weight here, I'm going to want to split that into two components. One perpendicular to the ladder and one would be down the ladder. And when it comes to the reaction R1, that will be split into two components, one in that direction perpendicular to the ladder and one up through the ladder like that. And then for the frictional force, that would be split into two components, one perpendicular to the ladder and the other one would be up through the ladder again. Now it's the ones that are perpendicular to the ladder are the ones that we need to consider. The ones that go along the ladder would produce no turning effect about A because those forces pass through the point A. Now to get these components, I'm going to need to put some angles in. And I always believe that you should work with the angle that you're given. So if that's the case, I can see that this angle up here is going to be 60 degrees. It's going to be 60 degrees because this line is parallel to the floor and what you've got here is a Z angle, alternate angles if you like. So that's taken care of that one there. In this group of forces here, the 60 degrees shows up as this angle in here. Okay? If you were to continue this round like this would be a right angle triangle. This would be 30 degrees, leaving us with 60 degrees there. 60 degrees also shows up in this place here. That's 60 degrees. That's because this is a right angle between these two red forces. So if this is 60, that would be 30. Then you've got a right angle here, and so if that's 30, that must be 60 degrees. Notice how I haven't written in the 30 degrees though. Alright, you can if you want to, but I tend not to. I tend to just work with the angle that I've got here. And so when it comes to resolving forces, remember that if a force contains the angle, it becomes the cosine of the angle. If it excludes the angle, it becomes the sine of this one. So in the usual way, when we take the moments about A, let's start, say, with the force R2. The force R2 split into two components then, we're only considering this one here, which is going to produce a turning effect about A in a clockwise sense. So its moment will be R2 sine 60 degrees because it doesn't contain the angle of 60 degrees, this one here. So it's going to be R2 sine of 60 degrees. That's the effective force that is wanting to turn the ladder about A in a clockwise sense. Its moment will be that force, R2 sine 60, times that distance back to A, which will be 2L. Okay, so that's the moment now of the force provided by R2 about A. Now we look at this component of the weight, okay? And that component contains the angle of 60 degrees, so this effective force here is going to be 20G cos 60 degrees. So we've got 20G cos 60 degrees, and this force wants to turn it in an anti-clockwise sense about A. As I say, just take a ruler to represent the ladder, put your finger at the point A and push in that direction, and you see that it will want to go round in an anti-clockwise sense. Okay, so that's going to be minus then, because it's in the opposite sense to what we've suggested here, positive for clockwise. Its moment though will be that force times the distance back to A, which will be that force multiplied by L. Now we come to these two forces, R1 and the frictional force F. they have no moment about A. As I pointed out earlier, that's the reason why I took it about A, because they pass through the point A, so they won't enter this equation. So it just gave me two forces to deal with. And because this is now the resultant moment is in equilibrium, there's no resultant turning effect about A, so that resultant moment must be equal to 0. Okay, well, I've got my third equation now. So I just need to do some substituting and clean this up. Now I can see that I can divide throughout by L, okay, in this one, so it didn't matter really what that value of L was, it just cancels out, okay. I could divide through by the cosine of 60 degrees. You don't have to do that, it just means you have less trigonometric functions to type into your calculator. If you divide by cos 60, you end up with sine 60 over cos 60, which is the tan of 60 degrees. So if I do that and just tidy this up, what we're going to have is 2r2 tan 60. 2r2, and I get my tan 60 degrees then by doing sine 60 divided by cos 60. There you go, tan of 60 degrees. When it comes to this term here, I've got just 20g left because the cosine of 60 degrees has been taken out. So we've got minus 20g equals 0. And so if I rearrange this, I could add 20g to both sides and divide by 2 tan 60. That would leave me with R2. So it follows from here that R2 must be equal to 20g divided by 2 tan 60 degrees. 2 tan 60 degrees then. Now, I know that g is 9.8, or I can take g to be 9.8, and if I work that out, I therefore have that R2 equals 56.580 and so on, which when rounded up to say 1 decimal place, that's going to be 56.6 newtons. So we'll just say that that equals 56.6 newtons to 1 decimal place, 1 dp. Okay, so that's given me my reaction then from the ground here, the floor. I just need to get the coefficient of friction, mu. Well, I can turn to this equation, alright? I can see, let's just call this equation 1. And I can say then that from 1, I can substitute this into this equation here. Let's just call this 2. From 1, sub in 2. I can equate the two together, so I have got 196 mu. So therefore we've got 196 mu equals R2. R2 being 56.580 and so on. So if I divide both sides by 196, I end up with mu equaling 0.288 and so on. And if I round this to 1 decimal place, I therefore have mu equals 0.3 to 1 dp. Okay, so I have all that I was asked for. Find the value of mu, the reactions at the floor and the wall. Okay, so I hope that's given you some idea then how we go about a question like this. Remember, look at the unknowns that you've got. In this case, 3 unknowns. It required 3 independent equations. That would mean resolving vertically, horizontally to get those 2 independent equations, and then 1 moments equation. And you can take moments about any point that you like. You could take it about this point here, you could take it even about the center here, or you could take it about the point A here. And I would strongly encourage you to have a go at doing this question again, where you do take moments about these points and check out that you get exactly the same answers. Alright? And that's the only way you'll gain confidence, I feel, in doing questions like this.